Welcome Chemistry 12-2. This is the second video for week 6. We're going to talk about Bronstead-Lowry definitions for acids and bases, and we'll take a look at some pH indicators. But before we jump into that, I just wanted to recap our Arrhenius acid-base definitions. Arrhenius was all about the H-positive ion and the OH negative ion. His definitions indicated that if a compound has an H and can create hydrogen ions when in an aqueous solution, they were classified as acids. And if a compound had an OH and could produce OH negative ions in an aqueous solution, they were a base. He later revised and indicated that some compounds, even though they may not have an H or an OH, they can manipulate water into gaining or losing an H and therefore produce hydrogen ions and hydroxide ions. Here are two examples of that. So we have an ion here, HPO4 -2. These were the last two examples we finished off with in the first video. I wanted to point out two things. Number one, I think I may have had a -1 for this charge in the last video, so I wanted to correct that. And I wanted to talk about how charges change in reactions. So this is PO4 -2. PO4, a phosphate ion, is -3, but this guy has an H with him, so he's -2. He reacts with water, and he's going to form an acidic solution, so we know that the hydronium ion has to be produced. The only way that's going to occur is if this water molecule takes this hydrogen away, and that's what's happening, and we have an H3O positive, and we have a PO4 -3. We're getting really picky now with our AQs when we're talking about ions and with our charges, and so that's something you may lose value with in the future if you don't record these ions properly. Down here, to create a basic solution, we have an ion very similar, but this time, see, its charge is -3, it doesn't have the H, and because it's going to create a basic solution, we know that we're going to have hydroxide ions. What does this water have to do to turn into hydroxide? It has to lose an H, and yes, this PO4 -3 gains that H and it becomes HPO4 -2. So I just wanted to point out, and this is a really good thing to remember when you're trying to decide what the new charge is going to be. This is generally the rule. When an ion loses an H, it becomes more negative. And when an ion gains an H, it becomes more positive. So here we were at -3, it gained an H, so we moved closer to neutral, closer to being more positive, and so it's a -2. So you can see there are some issues with Arrhenius and acids and base definitions, and so we're going to move into a second set of acid-base definitions, and they're known as the Bronstead-Lowry definitions. And Bronstead-Lowry are two different men, Johann Bronstead and Thomas Lowry. What was interesting about these two gentlemen is that they were not working as partners. They were working in independent labs in opposite corners of the world, and they came up with the same idea at the same time in about 1923. And so they really wanted to concentrate on the proton. And so they thought, you know, if we could narrow it down and just look at the proton as opposed to H plus and OH negative, we could simplify our definitions and they would probably be more wide-reaching. And so that's what they came up with. So the Bronstead-Lowry, or BL for short, the Bronstead-Lowry acid is defined as a substance that can donate an hydrogen ion. So any substance that will give away an H or donate an H is known as a BL acid. And a Bronstead-Lowry base is a substance that can accept a hydrogen ion. Okay, so if it's a compound that's taking a hydrogen ion, it's going to be a base. If it's a substance that's donating or giving a hydrogen ion away, it's going to be an acid. So quite simple, and also revolving all around the proton. So a very clear definition. It's a theoretical definition in the fact that they talked about what was happening, but they didn't talk about why it was happening. So again, they were just showing or describing the observations that they were making with their acids and bases, and the donation of an H or the acceptance of an H. They weren't talking about why acids wanted to donate that H and why bases wanted to accept that H. So a theoretical definition, not an empirical definition. The example below shows two substances that would not be considered a base and an acid according to Arrhenius definitions. Examine why these would be considered a Bronstead-Lowry base and acid. So we've seen this reaction several times. Hopefully you're getting more acquainted with it. We have ammonia here, we have water molecules, we have ammonium ions, and we have hydroxide ions. So would we call this acidic or basic solution? I hope you're saying acidic. No, I don't. I hope you're saying basic because it has the hydroxide ion there. And so we, with Arrhenius, we kind of got around it and we said, well, NH3 does not have any hydroxides, but when we put it in water, we can actually take one of those H's away from water, give it to the ammonia to become ammonium, and then we free up that OH negative ion. And that's how Arrhenius would describe this. But a more simplistic view is what Bronstead-Lowry would take. And that is, if you look at kind of the before picture, your reactants, and the after picture, your products, you'll see that NH3 turns into NH4. It's gained a hydrogen. And H2O turns into OH. It loses a hydrogen. And so it's just a more simplistic view, and you can see any compound that gains an H, okay, and any compound that loses an H. And so therefore, in this case, the water is going to be your Bronstead-Lowry acid. It's donating an H to whom? To NH3, and NH3 becomes the base because it's accepting that H. Pretty straightforward. Here, the same thing is in pictures, okay? Now, there's a couple other definitions that go along with it, but to be clear, it's just that simple. A compound that loses an H or donates an H is identified as an acid, and a compound that gains an H is identified as a base. One of the really big advantages to these sets of definitions as opposed to Arrhenius is that these definitions or these reactions are not tied to water. These reactions can happen in an aqueous solution, but they don't have to happen in an aqueous solution. Unlike Arrhenius. Arrhenius definitions had to happen in a water solution. They needed that aqueous solution in order to produce the ions. It's not necessary here with Bronstead-Lowry definitions. Let's look a little further. So this reaction, same one we were just looking at, ammonia, water, ammonium, and hydroxide. You can see it's got equilibrium arrows here, so it's an equilibrium reaction. So these two react to form these two compounds. But you might not have known, if you didn't get a chance to talk about gas laws in grade 11, what if we increase the temp? We know that temperature can wreak havoc on an equilibrium. So if we increase the temp, what happens actually is the NH3 is less soluble. So therefore we don't have as much NH3. So in fact, by increasing the temp, the concentration or the amount of this compound decreases. When that happens, we know that the equilibrium is lost. And we know, thanks to Le Chatelier's principle, that the equilibrium is going to shift so that it can fix itself. So if the concentration of ammonia drops due to a temperature change, this equation, or equilibrium rather, is going to shift left. And so I wanted to show you guys that the forward reaction is occurring and the reverse reaction is occurring at the same time. So we actually have two sets of acids and bases here, if you take a look at it. Okay? So overall, this equilibrium has two acids and two bases. So if we're looking at the forward reaction, we have a base here and we have an acid. The base is going to accept an H, and the acid's going to donate an H. But let's look in the other direction. In the other direction, this is our before picture, and this is the after. So before, we have NH4. After, we have NH3. It's flip-flopped. Here we now have an acid, and here we have a base. So we actually have two new terms called conjugate acid and conjugate base. And conjugate acid and conjugate base, okay, are basically the acid and base of the reverse reaction, if you want to think about it like that. So a conjugate acid, particles formed when a base gains a hydrogen ion, and conjugate base, the particle that remains when an acid has donated a hydrogen ion. So if that's confusing, thinking about forward and forward and reverse, a more simplistic way of looking at it is the before and after picture. So here, NH3 is a base because it accepted an H. So here it was before the H, here it is after the H. So it was a base, it becomes a conjugate acid. Particle formed when a base gains a hydrogen ion. So when this base does its accepting, it turns into a conjugate acid. The same is true for your acid. Here's your acid. It's going to donate an H. Well, what are we going to call it after it donates the H? Well, we could call it hydroxide ion, but to be more general, any acid, when it gives away its H, what's left over is known as the conjugate base. That can be a little confusing, so make sure you read this slide one more time. Okay, so here's our base, it's accepting an H. Here's our acid. Who knew that water would be an acid? We see that a lot now, because we see water accepting or donating H's all the time. So here's our base, here's our acid, here's our conjugate acid, because it's what the base looks like after it takes the H, and this is our conjugate base. It's what the acid looks like after. Now, you might remember that term, conjugate acid and conjugate base. We've seen it before, and where we've seen it before is with our acid-base table. I'm just going to bring this up so I can see our time. So with the acid-base table, remember we had a column of acids and we had conjugate bases here. So I hope you're not surprised when you start to look and see here's an HBr for the acid. Lo and behold, after it lost its H, it becomes Br negative. It's a conjugate base. Here's HClO4 maybe, and here it's ClO4. So when your acid loses its H, it becomes a conjugate base. When a conjugate base, or when a base gains an H, it becomes a conjugate acid. Okay? So you can see many, and they're called a conjugate acid-base pair, or for short, just acid-base pairs. So acid-base pairs, you can see them linked up beside each other on the acid-base table. Here we have, okay, a lot of people think this is the acid-base pair, and that is incorrect. The acid-base pair is the base and what it looks like after it gains an H, or the acid and what it looks like after it loses the H. So these blue lines are actually matching up the acid-base pair, okay? You'll always find acid and bases on the reactant side. You'll always find your conjugate acid and base on the product side. So here's a smaller version of our acid-base table, and you can see these acids and conjugate bases here, okay? So a conjugate acid-base pair, or sometimes just for short, an acid-base pair, it's when you are looking at the base and what it looks like after it, in this case for bases, it would accept an H, and for acids, it would donate an H, okay? So they have to differ by a proton, they differ by an H, NH4, NH3, H2O, OH, HCO3, CO3. Take a look at the charges as well. HCO3 is negative, CO3 is negative 2. Why? Because it's lost an H, right? It's lost an H, so it gets more negative. So some things to think about. When we take a look at a Bronstead-Lowry, again, here's a different equation, but we can use the same process. HCl, H2O. HCl turns into Cl negative. What happened? The HCl lost an H. Where did that H go? It went to water. So HCl is your acid. That's not a surprise. Base. Ooh, hold on. Didn't that... check that out. Here, H2O is an acid. Why? Because it donated its H. Here, it's acting differently. So depending on what it's matched up with, sometimes it's an acid, sometimes it's a base. Here, it's a base. It has to do with strength, and we'll talk about that a little later. But here, it's a base. And so the H2O becomes H3O positive. So we have a term for these substances that sometimes act like an acid and sometimes act like a base, depending on the situation. And the term is right over here, amphoteric. So amphoteric is a substance that can act as an acid or as a base in different situations. It comes from the Greek word amphoteris, meaning partly one and partly the other. I always think of biology and I think of amphibians, right? So amphibians, they live part of their life in water and part of their life on land. Or you can think about the amphibious bus that you can get in Ottawa, and it can go in water and it can go on land, right? Amphibious. So amphoterous means partly one and partly the other. An amphoteric substance can act as both an acid and a base. What makes an amphoteric airplane? Blah, blah, blah. Okay, so that's a new term for us, and we're going to see it more and more often. Sometimes it's called amphoteric, so a substance that can act as an acid or base is known as amphoteric. Water is a great example. You might come across this next year in first year chemistry, amphiprotic. What's the difference between amphoteric and amphiprotic? Well, there's a slight difference, and I wanted to point that out. For me, it really doesn't matter, but later on, if you move on into chemistry, you might start talking about the slight difference between them. Amphoteric, it's a substance that can act as an acid and base. Amphiprotic's a little more specific. Amphiprotic, remember, protic means protons. So amphiprotic is a substance, an anion, that can accept or donate an H. Okay, now they're saying kind of the same thing, and you're right. You can be amphiprotic and amphoteric, but sometimes you can be amphoteric and not amphiprotic. So amphoteric is when the two substances, or any substance, can act as an acid or base. Amphiprotic is more specifically a substance that can donate an H and can gain an H. So they can accept H's and they can donate H's. So there's a slight difference there between those terms. So when you take a look at your conjugate acid-base pair, remember, your pair, you're going to have one on the reactant side and one on the product side. So they're the two substances that differ by an H, differ by a proton. We're going to later on use our acid-base tables to talk about why this is occurring. But just a quick look here, you can see CH3COOH is aqueous. It's got a percent yield, right? A percent reaction of 1.3, a percent ionization of 1.3. We know this is really, 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 really weak. Okay? So because it's 1.3, it means that these, even though it's really, really weak, it means it's not ionizing very much. So it means that we have, we're favoring the reactants big time. We're favoring the reactants. So what that's telling me is that this guy right here, okay, is, it says the percent ionization is only 1.5, so the reactants are favored when equilibrium is reached. Just remember that the stronger an acid, the weaker its conjugate base. And conversely, the weaker an acid, the stronger its conjugate base. Okay, so think about this. What this is saying is that our acetate ion likes to hold on to its H. It doesn't want to give its H away. It likes to hold on to its H. And so we see this again, and I got rid of my acid-base table, and I should have not gotten rid of it right away. So bear with me here, guys. Okay, so here's my acid-base table, and what you can see, and we've talked about this before, our strongest acids, our 6 strongest acids are at the top, and then they decrease, come on, they decrease as we drop down the table. Well, now we know that as the acid gets weaker, its conjugate base gets stronger. So the strong acids are up here and they get weaker as we go, but it's opposite for this column. For this column, and we'll talk more about that in our third video, for this column, your strongest bases are actually down at the bottom and they get weaker as we go up. So strong acids get weaker as they go down, conjugate bases get weaker as they go up. Strong acids at the top, strong bases at the bottom. So we'll talk more about that in the next video, the strength. Just wanted to recognize again one more time, people often think when we talk about an acid-base pair, it's the 2 reactants or the 2 products. That's incorrect. A conjugate acid-base pair is the acid and what it looks like after it gives away the H, a conjugate base, and the base and what it looks like after it accepts an H. Okay? Very quickly, we do have a third set of definitions. The definitions for acids and bases, the third set we talk about is Lewis acid and bases. Now, it's really not part of the curriculum for 12-2 chemistry, so I'm just going to briefly mention it just so that you have a complete picture. Gilbert Lewis, around 1930, and he was, instead of looking at protons, he looked at electrons, so he looked at it from a different point of view. So with him, instead of having a proton being donated or accepted, he had electron pairs. So a Lewis acid is a substance that can accept a pair of electrons. So they were electron acceptors and bases were electron donors. So opposite and with electrons instead of protons. Again, just want you to recognize that there are a third set of definitions that exist for acids and bases. This is a great summary table, and so you could take a picture of it, or these slides will be available for you, so you could take a look through the PDF. And this one is nice because it's got all three definitions here. H plus producers, OH negative producers. The limitation here, it has to be an aqueous solution. Okay, Bronstead Lowry doesn't have to be, can be an aqueous solution, but doesn't have to be an aqueous solution. Proton donors are your acids, proton acceptors are your base. Lewis, they're flip-flopped, and they're talking about electrons. So electron pair acceptors, electron pair donors. So quickly, if you look at Lewis diagrams, this is the best way to think about it, okay? Identify the Lewis acid and the Lewis base. If you remember that a Lewis base is the one that's more negative. So if you can find the most negative substance in your reaction, that's your base, the other one's your acid. Here you can tell right away, H plus, it's positive, it doesn't have any electrons. And over here we have oxygen with two unshared pairs of electrons. So this is more negative, it becomes the base. And this is the acid. Down here, this guy's neutral, this guy's -1, this guy's the base. So that's a really good thing to remember with Lewis acids. And it's the same guy, Lewis dot diagrams, what I just said. We did those in grade 11, so we drew Lewis dot diagrams a lot. So when we were drawing Lewis dot diagrams, we were drawing electrons, right? We're using dots for electrons. So it's no surprise that he used those electrons to also define his acids and his bases. If we take a look at this one, it said, would you predict PCl3 to be a Lewis acid or a Lewis base? So here, this picture might help. Taking a look at this picture, you can see the phosphate has those two unshared pairs of electrons, right? And it's going to be a base because it is more negative. All right, one last thing. Trying to keep this video short because I know the last one was a little longer. So the last thing I wanted to talk about, and it won't take too long, is I wanted to talk about pH indicators. And pH indicators are substances that change color depending on if they're in an acidic environment or a basic environment. Okay? So this is actually the second part of section 19.3 in your textbook, page 609. Substances that change color when reacted with acids and bases that are made from a conjugate weak acid-base pair that are distinctly different colors. So some of our acid-base pairs, Bronstead Lowry, acid-base pair, so an acid and its conjugate base or a base and its conjugate acid. Some of these pairs differ in color. And so when it's in its acid form, it's one color, and when it's in its conjugate base form, it's a different color. Here is just a very generalized equation we use for indicators. In for the indicator, H to tell us that it's in its acid form, right? Because it's going to be the donator of H. So HIN is a general formula for indicators, and H here is going to, because it's going to be an acid, it's in its acid form, it's going to donate that H to water. And when water gets that H, it turns into H3O positive, and when the indicator loses that H, it turns into IN negative. Remember, it's neutral over here, lost an H, so it gets more negative. So this is a general formula, or general equation, I should say, for an indicator in action. So here's the pair. So we have our HI, let's see if I can do this, right? So our HI and D, so that's our pair right there, those two. Okay, and here's our other pair right here, which I really don't need to know, but that's our other pair. So those are our two conjugate base pairs. Litmus is a great example of an indicator. So when litmus, so you could put HL if you wanted for litmus. So when litmus is in its acidic form, it is red, which shouldn't be a surprise. And when it's in its basic form, or conjugate base, it's blue. Now, it's kind of neat because we can jump back and talk about Le Chatelier's principle with this. Just checking my time. All right. So, if you think about Le Chatelier's principle, it'll kind of explain why they flip-flop back and forth. It's an equilibrium, so they're shifting left and they're shifting right all the time. If they shift left, it's going to be red because this, it's producing more of this HIN. If it shifts right, it's going to be blue because it's producing more of this IN negative. So when you look at Le Chatelier's principle, the first one's pretty straightforward. Here's our equation up here, and we're going to dump in some more H3O positive, right? So if we increase the concentration of H3O positive, you'll remember from Le Chatelier's principle, the fix will be to try and decrease it. And it's going to be that reverse, that shifting left. And when it shifts left, it makes more of your red. Okay, so when litmus is put into a acidic environment, it turns red. If you want to think about a basic environment, okay, we're still going to stay with the the H3O positive because that's what's in our reaction up here. But what happens in a basic solution is, you're right, it's the OHs. So we're dumping in more of those OHs. How are they going to affect the H3O? Well, what happens is when these OHs are dumped into the beaker, they react with the H3O to form water. So there's kind of like a back reaction happening here. The OH reacts with H3O positive to form water, which is neutral. But the decrease in H3O positives has effect on this reaction. On this reaction, when we dump in extra OH negative, we essentially decrease the concentration of H3O positive. Therefore, the fix would be to make more of it. So it has to shift right to make more of this. And when it shifts right, it makes more of the conjugate base as well, and therefore we get our blue color for base. So that's just kind of a neat throwback to Le Chatelier's principle to explain how your indicators work. And so there's lots of different indicators. Actually, you have on the back of your periodic table, so if you want to take a second, pause and find your periodic table, if you look on the back of your periodic table, right at the bottom, you're going to find a chart that looks like this. I just kind of copied a little bit of it, but you're going to find a chart that looks like this, and it's called your indicator chart. So it should be easy to find. If you want to pause and find that, you should. And we can use that to help us when we talk about indicators. So Le Chatelier's principle again, if you're in a acidic environment, the concentration of H3O positive goes up, we know that. And therefore, the fix is to decrease it, shifting it to the left, making more of this, and therefore you get a red color. If we put it in an environment that's basic, we've got a whole bunch of extra OHs. So they kind of create a background reaction. They take the H3O positive and they react to make water, which is neutral. So essentially the concentration of H3O positive drops. When it drops, the fix is to make more of it. So this would shift to the right to make more of it, and also making more of this indicator in its conjugate base form, and therefore we get blue. So how can we use this to help ourselves out? Well, what we can do is we can actually use different indicators to try and narrow down the pH, because that's, I maybe should have told you a little bit about this indicator table. The indicator table works like this. So here's some common indicators. And the first column here, as you can see, it's instead of HIN, they're actually putting in letters for the indicator. So this is HMV for methyl violet. This is, I don't think we have litmus, yeah, litmus, HLT for litmus. So they're using the general HIN, but putting in which indicator it is. Here we have a color of the HIN. So when it's in its acid form, what color does it form? And when it's in its base form, what color does it form? And this is actually a range. So what we mean by the pH range is this. This is how it works. If I use orange 4 and I get a red color, the red tells me that it's in its acid form, which means that the pH of the solution is less than 1.4. This is the in-between. So if it's red, it's less than 1.4. If it's yellow, it's greater than 2.8. And if it's somewhere in between 1.4 to 2.8, we get a combination of these two colors. So red and yellow, I think, is orange. So we get an orange color that's in between its range. Okay, so for example, litmus, the bottom one down here, if your pH is, if you get a red color, we know that the pH is less than 6. If you get a blue color, we know the pH is greater than 6. If you get a in-between color, what would be in between blue and red? Purple. If you get a purple color, you know it's between 6 and 8. So that's how this indicator chart works. Now, how could it help us out? Since different indicators have different acid strengths, the acidity or pH of a solution at which an indicator changes color varies. They are mentioned in a table on the, proofread my stuff, back of your periodic table. So here's an example. What if we had a solution, and so we poured it into 3 beakers, and we're going to use orange 4 in one of the beakers. We're going to use methyl red in the second beaker, and we're going to use Congo red in the third beaker. So it's the exact same solution. I've just broken it up into 3 beakers so we could use 3 different indicators. So when I put the orange 4 into the solution, it turned yellow. So what is that telling me about my solution? Well, if we go down here and find orange 4, okay, it turned yellow, so keep on going. It was yellow, so that meant it was in its basic solution, or its basic form, its conjugate base. So that tells me that the pH is greater than 2.8. Now, by using more than one indicator, we can kind of narrow the range of the pH of our solution. There's other ways of finding the pH of a solution. This is just one. So methyl red is red. We find methyl red. It's right down here, right? Oh, it's red. It's in its acid form. And so we know it's less than 4.8. So it's greater than 2.8. It's less than 4.8. So that's a pretty good range. That's a range of 2. The last one, Congo red, is blue. So if we find our Congo red, we find that it's blue. We know that it's less than 3. So we've actually closed the gap even more. It's less than 3. Okay, so now we have a range, a pretty small range, because we know it's greater than 2.8 and it's less than 3. So we've got a 0.2 range for our pH in that solution. All right, so that's all I have to say. I just wanted to let you guys know a little bit about Bronstead-Lowry definitions, and I wanted you guys to know a little bit about indicators, pH indicators. In your assignment, questions 1 to 11 have to do with acid-base definitions and pH indicators, questions 1 to 11. Thank you very much for your attention.